Hello, ladies and gentlemen, and thank you for joining me. We're looking at our last question, that is question B3 on our 2017 Canadian Senior Paper. Now, fair warning, B3 is every year the hardest question on the senior paper, just like B3 is the hardest paper on or hardest question on the intermediate paper, and 10 is the hardest question on the Euclid and those sorts of things. And I would say B3 and Euclid 10 are about the same level of difficulty. So, if you don't have enough Canadian senior papers to practice and you want to get good at B3s, try some Euclid 10s, or vice versa. If you're practicing for the Euclid coming up in April, try a few of these B3s on the Canadian senior paper. They're all quite challenging. What have we got here? So we got an A, B, and a C part. So A, consider a function f, where f of 1 is equal to 2, and we know f of n is f of n plus 3n for all positive integers n. So, for example, when we sub n equals 1 into the equation, you get f of 1 is f of 1 plus 3. And since we are already told f1 is equal to 2, we see f of 2 is 5. Continuing in this way, figure out what the value of f of 26 is. Okay, and just slowly glancing down below, I see the word function a few more times. So this seems to be what the question is based off of, is we're going to have functions, we're going to have to deal with properties. But I don't mean functions like, the quadratics you're used to or anything like that, or maybe, a weird exponential function. These are functions where we're likely going to be given sort of single properties. Just looking ahead, I can see these, and we're going to have to deduce certain things about the functions. And these questions can seem a little scary. Usually, just because I mentioned the Euclid a moment ago, usually the Euclid paper has a question involving, a function and a given property. So these are not uncommon on questions or on contests. So let's dive into this one with part A. So how can we work out f of 26? Well, we really only know two things about our function. This property that satisfies, and that f of 1 is 2. And I guess now we worked out that f of 2 is 3. So we really are sort of limited. We don't know a whole lot. Just write down the property. It's f of n plus 3n. Okay. So, well, what can we really do? Well, I don't know, say, f of 3 or f of 4 or anything like that, but we can say something like let n be 2, because I know f of 2. It's 5. Okay, and so now we see that we've got f of 5, and you'll notice this number is getting bigger, is 5 plus 6. It's 11. Okay, so now I could take 5 and I could plug it in. You could say f of 5, so that's really going to be f of 11. Okay, and that'll be f of 5 plus 3 times 5. So that'll be 11 plus 15. So that'll be 26. And that's kind of nice. When we see that, we think, oh, great. If I do this one more time, then I'm just going to need to, I'm going to get the f of 26 that they're talking about. Fantastic. So let's do it one more time. F of 11 is f of 11 plus 3 times 11. That's really f of 26 is 26 plus 3 times 11. And so that's 26 plus 33. And so we're looking for an answer of 59. Okay. That's a written question. We have shown our work, but I would probably summarize there at the end. There's my answer. F of 26 is 59. Great. Okay. Now, we're done with A. How about B? So, as I've already sort of looked ahead, we do have functions and a property. So, what do we got here? Prove that there is no function g that starts with g of 1 is 2. Very similar to what we had in the last one. But we've got a very different looking property. G of n plus m is n plus g of m. So that's kind of interesting. Applying g sort of undoes the g here and puts a g here. At least that's the way it sort of looks. Prove that there is no function with that property. Now that's kind of interesting. Because if we think about it for a moment, there is a function that has this property. You know, if just let g of x be x, and then g of n plus m is just g of n plus m, which would just be n plus m, but that's the same as n plus g of m because g does nothing if it's this function. So there are functions that satisfy this property, but they apparently don't also satisfy this property, and this one doesn't. That would be g of 1 is equal to 1. So somehow this property and this property, they are incompatible. Okay? So how do we approach something like that? Well, we could try and proceed a little like we did in the last one, working out different values of, I guess, g. You know, we could probably figure out what g of 2 is, maybe, or something like that, and try and maybe reach some sort of contradiction. Now, what would a contradiction here look like? Well, probably, since we're starting with a value here, probably if I could find, you know, g of 10 is equal to 30, but then do the calculation in a different way and get g of 10 is equal to 29, something like that. Getting two different values for the same input would mean that there is no such function. But either way, I think probably the best approach is let's start by assuming. So let's assume such a g exists. Okay? We're going to assume this towards a contradiction, and sometimes it's a good idea to tell people, I'm going to try and make sure that this, I'm going to try and find two properties that conflict. I'm going to try and get a contradiction here. Okay, so what do we know? We know g of 1 is 2. And then we've got g of n plus m is n plus g of m. All right, now, planning ahead with this, if I'm going to actually start computing values, I need to know what g of m is. I mean, the n doesn't matter, but the g of m does, so we're going to have to let m be 1. But I also want to know what my input to g is, so I should probably also know what g of n is, so let's make n equal to 1, just to start off. Okay, so yeah, g of 2 plus 1 is 1 plus 2, so really we've got g of 3 is 3. Okay, great. Now we're skipping over g of 2. Maybe there's a way to get g of 2 somehow coming back to this, or maybe we just press on. Maybe we'll get two numbers that don't work with something like g of 5. I don't know. Okay, but we do have another number to work with. So now we could do things like make n1 and g3. We can only use n's and m's that we have g's for. Otherwise, you're going to have quite a mess. Like we can't do g of 2 plus 3 because I don't know what g of 2 is. So that's making it too difficult for ourselves. So, we can try both of them. I don't really know which one's best. So let's be clear to whoever's marking. So now let's try m equals 1, n equals 3. So we get g of 3 plus 1 is 3 plus g of 1. And so that's going to be g of 4 is 5. 3 plus 2. Okay, so that gives me another one that I could work with. But before we get too carried away with it, let's try m is 3 and n is 1. And you could also, I'm just, as I'm thinking about this, make a little table of values, or a table to just sort of sort out what you have and haven't done already. So you get 1 plus g of 3. So this will be g of 5 is 4. That's kind of interesting. So I wonder if there's a way, maybe something like 9, if there's a way to make 9 happen. So maybe g of 5 plus 4. No, that would be 8. Oh, okay. So now, do we keep building up? I've got g of 1, I got g of 3, I got g of 4, I got g of 5. We're missing g of 2, but I mean, that's not necessarily a problem. Now I know g of 5 is 4. Now, hold on a second. Could we do g of... I did g of 3 and 2, except I don't know what g of 2 is, so I can't do anything like that. Could we do g of 5 plus 1, because that would be a 4 plus 1, that would be g of 5, must be 5 plus g of 1, which is 2, and I've got g of 4 plus 1, so g of 5 is equal to 7. So this wouldn't work out properly. Yeah, so there's our contradiction. Let's backtrack. We'll do it a little more carefully, and we'll write it up the same way we would want it to be written up. Okay? So it looks like I don't really need g of 4 is 5, but okay. We'll say, but now. And it's kind of interesting that the first time this happens is the first time the function has an output that's less than the input. That's kind of interesting. But now letting n equal 5 and m equal 1, we see g of 5 plus 1 is 5 plus g of 1. So g of 4 plus 1 is 5 plus 2. G of 5 is equal to 7, which contradicts what we just worked out with g of 5 is equal to 4. All right? We just worked that out up here. All right? So it turns out we didn't actually need this one here, but we didn't know that at the time. We were just experimenting around with it. Okay. So g1 is 2, g of 3 is 3, and so you could probably write this up a little nicer and neater now, knowing which one you don't need, but that's something. So I would recommend you write in pencil on the booklet quite lightly, and then you could come back and remove things like that. It just makes the solution flow a little nicer. But it's more important that you get your answer before you go back and tidy something like this up. Now, when we try C and get stuck at some point, and we probably will, because C is probably as hard as the paper is going to get, we might take a little break and go clean up A and B, or clean up earlier questions like B2 or B3, or sorry, B2 or B1, because that's where the writing matters. Okay. What do we got for C? Prove there is exactly one function h with the following properties. Okay. All right. What do we got? Domain of h is the set of positive integers. That's not hard. H of n is a positive integer, so it goes from positive integers and outputs positive integers. Fine. And then we have a property suspiciously similar to the one we saw up above, h of n plus m. So it kind of looks like h cancels out another h, distributes over addition, and then seems to add in an extra 1. That's just sort of a way to read what this is doing. For all positive integers n and m. Okay. So there's going to be two parts to this question. We're probably going to have to find the one function that satisfies this and quickly show that it does satisfy these properties. And then we're going to have to show that that can be the only one. Now, that's not the only approach to this sort of question, but I find that for something like this, it's probably the most helpful. One thing you could do is just say, well, let's look at these three properties and just argue and argue and argue and argue, and then suddenly we get h of x is x, or whatever it's going to be. X squared. I don't know what the function will be. And you can do that, but it's a lot easier to just try and find the function. And I find for questions like this, which actually don't happen a whole lot on Waterloo contests, but they do happen on other papers. Things like Canadian Math Olympiads, or really just sort of any Olympiad level paper, you can find a question like this out there. And I found for questions where they say prove there's exactly one function or only one family of functions or something like that, usually the one function is very easy to spot. Usually it's something simple like h of x is equal to x or something like that. And knowing that that's the only solution, you can take a look at it, draw inspiration from it, and try and use the properties that function has and the properties that you are given to sort of eliminate everything else. So let's take a little bit of time and see if we can find the single function h that's supposed to do this. So you go from positive integers to positive integers. That's fine. There probably won't be any halves or square roots in our expression. But let's focus on our property. So h of n plus m is 1 plus n plus h of m. Now, if this were just a simple h of x is equal to x, that would satisfy the first two properties. But there's this annoying little plus 1 here. And so it can't just be h of x is equal to x. But, well, what would we need to have? So h of 1 plus 1 would need to be 1 plus 1 plus h of 1. And you'll notice, hey, those are the same, and it looks like we just added 1 to our input. And come to think of it, if I put 2's and 2's in here, you just add 1 to your input. I mean, these two swap around, but you're still ultimately adding 1. So let's see. Would something like h of x is equal to x plus 1 work? Because that's a nice, fairly simple function. So let's see. H of n plus m would be h of n plus m plus 1, because that's my input, that's my x. So there's that plus 1. And then h of n would be n plus 1. But then I can take this m plus 1, and that would just be h of m, which is exactly what we want. Okay, so you'd probably, if you want to do this, and you'd probably get a mark for finding this h, maybe even 2, depending on how you write it up. But here's what we'd probably say in the question. We claim h of x equals x plus 1 satisfies the properties. Okay? And you just run through the list, and I'd say, you'd say something like if x is positive, x plus 1 is still a positive integer. That really takes care of the first two properties. I mean, technically you should say h of x equals to x plus 1 defined only for inputs where x is positive. No one cares. Okay? The first two properties are just sort of saying you're sticking with positive integers. I would guess maybe because there's probably some trickery if you're allowed to use zeros, but I'm not sure. I mean, certainly if I could let m be 0, that would make this a lot more interesting, but okay. So, yeah, domain's positive integers, send it to positive integers, fine. But then here you show, okay, for any n and m, and basically you just copy the same thing I wrote over there, or on the last page. Add m plus 1, and then you say, that's n plus 1, that's m. And you could add in a little more bracketing just to really show what's going on. Rebracket there. And then, since addition doesn't care the order in which you write things, there we go. And so that satisfies that property. Good. We have found the one function they're looking at. But now, and this is probably the hard part of the question, why is that the only function that does this? Okay, we've got a pretty unusual looking property here. Start here, we end here. I mean, how can we really get a handle on this? This is an unusual sort of expression, And that's always how these function questions go, especially when they're harder ones on more advanced math papers. How do we actually deal with an expression like this that we haven't really seen, and it's quite sort of entangled. I don't like the fact that the h is being applied to other h's. It makes it really hard to use. So what can we do? Well, having identified that h of x equals x plus 1 is the function we're looking at, what we can do is we can say, all right, what properties does this have that I might be able to show from this property here? It sort of really isolates it. What makes this function special? And you could say things like it's always increasing. You plug in h of 2, you get h of 3. Can I show that this expression should always be increasing? Because then that would cut out a whole lot of other functions that are decreasing or just don't always have the values going up and up and up. Right? Other things we could say, well, hey, this is technically a line. Not only that, it's a line of slope 1. So we might turn this into a graphing thing. But one of the hard parts of using the property that they give us is the fact that it's got sort of two inputs. And that can be hard to work with because we're trying to talk about just a single function, h of x equals blah. So what you might want to do is find a way to sort of turn this into just a one function, no m's and n's. So something you might be able to do is say something like let n and m both be the same value. Then you'll get h of x plus x is 1 plus x plus h of x. And that's good. I mean, this is sort of what we were playing around with earlier to make us realize what the function was. Okay? But there's not a whole lot that can really be done with this unless you manage to show something like for every positive integer y, you can always find an x so that this is true. Because then what you've managed to show is h of y is 1 plus y. You'd have to be able to say for every y. And I don't think that's possible. Because the smallest x can be is 1. So and since it's got to be 2, it has to be 2. You'd have to show that. The smallest you could do would be y equals 3. And so that wouldn't show it for everything. But that is certainly something to think about. Is there another way to sort of get a better handle on this? Well, we know, so we don't necessarily want to do that. I don't think that's going to help us right now. We could say something like, we know for a given x, h of x is positive. So we could try and say something like maybe let n be x and maybe m be h of x. Right? This still sort of is it's taking my m and my n and basing them on a single thing x, some single fixed value x, let's say. But watch what happens. Now I've got 2h of x's inside. That's going to boil down to a single 2h of x expression. Unfortunately, we get an h of x outside, and you already heard me remark, I'm not the biggest fan of h of h's. It's kind of hard enough to work with h only from the basic property as it is. So we can, but at the same time, this gives me an expression for h of 2x, or sorry, h of 2h of x. Okay? And so, well, if we tried to do something similar, n being x and m being h of 2 h of x, or how about we try 2 h of x? Right, because then you'll have h of x and 2 h of x's, And those will add up to be 3h of x's. You'll see this is all just in terms of a single x now, so that makes me a bit more comfortable. And what do we get here? We still get a 1 plus x, but now we get h of 2h of x. But we just figured out what that was over here. So you get 1 plus x, and then 1 plus x, and then h of x, which I still am not happy with h of x, but we get this sort of an expression, and now we could probably do the same trick. So this is at least something we can work out. We'll do it quickly because I don't know if this is the property we need or if we're going to need to go back for something else. But I claim, what do we want to claim? Let's say h of, I don't know, k. H of k of h, well, say k plus 1 of h of x is going to be k plus k of x plus h of x. Yeah. Okay, so we see this is true for k equal to 1. We did that over here. And 2. So these are nice little base cases. You would just do a quick induction. So if you let n be x and m be k plus 1 h of x, then h of x plus k plus 1 h of x is going to be, so this thing here is, we've added one more x. We get 1 plus x plus h of k plus 1 h of x. And so by induction, so you would assume that it works for k plus 1. Well, now we're showing it's true for k plus 2. Nice little induction argument. So we get k plus kx plus h of x. So k plus 1 plus 1 of x, h of x. So by the principles of mathematical induction, our property holds. And so that's true for a nice given x. I don't know how this is necessarily going to help us, but at least we have a nice single input over here, although you'll notice we kind of have, now we've got these k's here. So what can we do? Well, for any, let's say, positive integers a and b, we can see we've got h of a plus 1 h of x, whatever the heck h of x is. It's sort of like h of x is turning into a nice constant. Maybe we'll call it capital X or y or something. I don't know. But that's a plus a of x plus h of x. And then we've got a lot of similarity here. And I don't know what h of x is, but maybe I could subtract these and cancel it out. And so we'll get, the difference in those two is going to be a minus b plus a minus bx. So I guess, that's an interesting expression, and it really sort of looks like a fairly linear thing. Because one of the nice things about linear functions like lines is addition and subtraction sort of easily come in and outside of the function symbol, h's and f's and so on. I don't like that it's a plus 1, but it's a over here, so here's something we can change. And actually, we could take out a factor of 1 plus, we could take out a factor of a minus b, but a minus b is the same as a plus 1 minus b plus 1. And so now it's the same sort of input, a plus 1 on this side, b plus 1 here, a plus 1 here, b plus 1 here. Okay. Now, if we take x as sort of a nice given, we haven't chosen anything about x. X has been generic through sort of all of this. So I don't wanna mess with that yet. Although I wonder, is there a way to get rid of this h of x and just talk about x? Or is there a way, because this is straying this is a very different expression than the one we started with, and it's not really looking anything like, can we show that the function's increasing from this? Or it's kind of linear. It's not quite, but it's kind of linear. So if I do something like this, divide by the a plus 1 minus b plus 1, you're left with 1 plus x over here, a nice constant. And this looks fairly similar to sort of slope calculations. Except a plus 1, b plus 1, these are not my inputs here. My input into the function h is a plus 1 h of x. But that can be remedied by dividing both sides by h of x. And so we might be able to show that any h that satisfies this must be a line. And that would certainly narrow things down, just like showing that any h that satisfies those properties must be increasing would also be a nice thing to do. So, but if you divide by h of x on both sides, I can write it like this. And so we sort of have a line. It's a line if your input looks like k plus 1 h of x. And this is true for any x. Okay? So certain parts will look like certain lines. And I guess now our next argument might be show that we get the same line regardless of x, maybe? Okay, so what do we want to do from here? This is nice. I like this. I feel like this is in a good place right now, but where do we go? What can we say? We can say then the function, let's maybe call it I of y defined by h of y plus 1 h of x. Well, let's call it I sub x, because x is given. X is fixed. So I sub x of y is a line of slope x plus 1 over h of x. At least when it comes to inputs y that are positive integers. So actually, let's not call it I, let's call it L, because we know it's a line now. Okay? So L of xy is a line, and this is true for any x. Let's just call it L sub x. So L sub x is a nice little line, but we get lots of different ones. So where can we go from there? Well, okay, so let's try and show that we get the same line. So let's start with different ones. Let's say x1 and x2. as fixed. And we get lines L of x1, L x2. Now they both have slopes, x1 plus 1 all over h of x1, and x2 plus 1 all over h of x2. But I would need to show they're the same line or they have the same slope. So how do you do that? Well, to show two lines are the same, we could show they have the same slope, but I'd need to know more about h of x. And you'll notice we've got h of x over x plus 1. That's kind of important. Maybe we need to show that the slope has to be 1 for all of them. And then that would definitely finish off our result. How else can you show line? Well, if you have 2 points in common, because obviously you can have 2 different lines that intersect, but you can't have 2 different lines that somehow intersect in 2 different places. So it would be enough just to show I've got 2 points that are in common to both of these lines. So our line looks like h of, now if it's the line lx1, you got to have an h of x plus 1. We also probably want an x2 in there so that I can sort of swap the order of these two. And then we need something else. So let's say something to the effect of we know, so to show these are the same lines, let's show they have 2 points in common. Okay. So we know h of x1 and h of x2 are both positive. So 2 of, so let's not say greater than 0, let's say greater than or equal to 1, because they have to be positive integers, right? So 2 times them is at least 2. Okay. So then, and also let's say 3 times them is at least 3, but I just need 2 points here. So 2h1 of x minus 1, 2h2 of x, sorry, h of x2, and h of x1 minus 1, 3hx1 minus 1, 3hx2 minus 1 are all at least 1. So they're all positive. So here's my point. Let's say lx1 of 2 hx1 minus 1 is equal to, sorry, 2x2. I don't think this is going to work here the way I want it to. So what I wanted to do was, because it needs to be the same point, so it needs to be the same input to both lines and have the same output. And the way I was doing it was just going to give me, I was going to start with 2 different inputs. Okay, so that didn't work. That's because I wasn't thinking right. Now, it's that darn plus 1 it's causing me an issue. That's what I don't like, is the plus 1 here, because that's what I was trying to subtract to correct, so that I would just get h of some multiple of h of x. And that's not going to work. So maybe I should change my lines a little bit. So maybe if I do L of x, y is h of y, h of x. So let's scrap this, and we'll start over again. So I don't like this. I'm going to redefine my line. All right, so let's say we see the function. I'm going to call L of x of y is equal to h y h of x is defined for y greater than or equal to 2. That's not really going to matter so much to me. And is a line with slope x plus 1 over h of x. So we're going back in time. We're just rewinding the clock back to when we made this observation. I'm just redefining my line because I don't like this plus 1. Okay. So for 2 given x1 and x2, we claim Lx1 and Lx2 are the same line, and we'll show it by finding 2 points they have in common. Because 2 points determine a line. Okay. No, that's not going to work either. Because that stupid h of x thing here. So I'm still not defining my line properly. Maybe this isn't the right approach. Maybe I can't do this with a line. So let's say this is a line for any y equal to 2h of x, 3h of x, 4h of x, and so on, with slope equal to. So let's phrase it a little differently. So the function h of y, I guess we're saying, is a line called L of x of y when we restrict to inputs of the form 2h of x, 3h of x. Now I can put the same thing into my line. And so in general, kh of x. Okay? So we'll find 2 points in common. So let y be, let's say, 2h x1, hx2. Okay? This input works for both lines. Okay. and both have output h of 2 h1 or h of x1 h of x2. Okay. Indeed, y equal to any thing that looks like the. I was just going to use x3, but we can just make the opposite. Or I was just going to use 3 in front here, but we can make the observation it works for any input like this. So indeed, y equal to this is an input for both lines. So these lines here have the same slope. As they agree on infinitely many points. Doesn't need to just be 2, we'll say infinitely many points. But if you wanted to stick with the 2 points that we set up, just use 3 hx1, hx2. Okay. So our conclusion is, if they got the same slope, this must be true. Okay. But moreover, we see for any x, 1 plus x over h of x is sort of some constant. Maybe we could call it c for constant. Okay. So that tells me, so multiply by, multiply both sides by h of x, divide by c, so then we can see h of x must be 1 over cx plus 1 over c. Okay. And we can do this, by the way, because since x was never specified at all, we always kept x. So it was just some variable in there. It's because it started because I didn't want to deal with an n and m at the same time. Okay. So we've got this. Now it's up to us to show that c, I guess, has to be 1. But this would probably be worth a lot of marks. It's probably just a little extra argument to show that c has to be 1. Now, what exactly can we do? Well, we know the output has to be an integer. We know h of 1 is an integer. So h of 1 is 1 over c plus 1 over c, so that's 2 over c. So c has to divide 2. In fact, it's a positive integer. So c is 1, which we know works, or 2, which we now need to reason does not work. And maybe we'll have to use part B here. So maybe h of 1 is 2. How can we rule that out? So let's see. If h of x is a half x plus a half, well, consider x equal to 2. H of 2 would have to be 3 halves, but the outputs must be positive integers. So our c here has to be 1. Okay. And we get h of x is equal to x, which we already knew all along. Or if you hadn't done the work that we did so long ago and worked out that this one works, we would now say, all right, having deduced all those properties, now we will check that c being equal to 1, h of x being x plus 1 does indeed work. But we wouldn't have thought to rearrange some of these expressions, something like this into slope form of a line if we hadn't known that 1 plus x already was going to be the right answer. So it was important for us to play around and try and find h of x that one function that would work first. It really guided a lot of what we were doing. We knew it had to be a line, and that's why we started messing around with lines back here. It took me a while to find the right expression I wanted. And then we found that they really had to be the same line. And that definitely helps. And there we go. You could then say which we know works. And there we go. That took us quite a while there. But we managed to get ourselves the proper answer. Okay. So that was it for B3. Very interesting. We don't usually see on Waterloo contests these sort of you'll see function questions. You'll see functions like this, or even the occasional one like this, but show that this class of functions, that there's only one function that works, or that sort of thing. That's usually something you find on a harder paper. So kind of interesting that we got to see one of these on a Canadian senior paper. But that's it for our 2017 paper. Thank you guys so much for watching. If you have different approaches to this or any of the other questions, feel free to leave a comment down below. Thank you for watching. Feel free to like or subscribe if you want to be kept up to date, but absolutely no pressure to do that. And I'll see you for more math in the future.